or good evening to everyone joining us today for this webinar. We would like to thank Professor Eric Mackay, our invited speaker, the EAGE Technical Community and CCS for organizing this event, and all of you for being here. We hope you enjoyed the session, and learn a lot. And with that, we will begin the webinar. Farnam, I hand it over to you.
Farnam, you're muted. We can't hear you. Sorry.
Okay, can you hear me now?
Yes, now we can hear you. Thank you.
Okay, yes, excuse me. So welcome everybody. Here is the second webinar from webinar series of all related to the CCS from technical community of the EAGE and CCS. And we are honored to host Professor Eric Mackay from University of Heriot-Watt. And the title of the presentation is CCS in Mature Hydrocarbon Basins. Lesson learned, things to avoid, and some synergistic opportunities. First of all, I will, as the agenda of the presentation, I will go with the introduction to the EAGE Technical Community and CCS, who we are and what we do. And then we go to the presentation, and at the end we would sum up everything with the Q&A part. So we are members all interested in developing CCS, making it faster and also safer to achieve net zero and also negative emission if it's possible. So our activities are all related to the subsurface, mostly in the CO2 storage, site selection, development and optimization, subsurface CCS monitoring, drilling and well integrity, de-risking for having a safer operation, and of course transparency for the public and other related activities that help us to achieve our goals. So in CCS committee, we are 20 members from almost all around the world, from US to the Europe, East Asia, Southeast Asia, and also Australia. And our community activities are different from participation in that, for example, the EAGE annual and the GET conferences. There are dedicated sessions and also workshops, and also educational and networking events and collaboration like this kind of webinars that, as I mentioned before, it is the second one, and also other news, career advice, and vacancies. So we are also participating actively in the next EAGE annual in Aberdeen, UK in June, and we would be happy to meet you there. So I hand everything to Professor Eric Mackay to start the presentation. Thank you.
Thank you very much for the introduction, Farnam. Let me just share my slides. Can I check that you're able to see the slides?
All good.
Good,
Yes.
thank you.
We are.
So thank you very much for the opportunity for being able to give this presentation. Thank you for all of you who've attended. My name is Eric Mackay. I hold something called the Energy Simulation Chair in CCUS and Reactive Flow Simulation at Heriot-Watt University. And we're going to be talking about CCS in the context of mature hydrocarbon basins and discuss some of the things perhaps we can learn, some things to avoid, and perhaps some opportunities that we should be thinking about. So the basis for all of this activity is rooted in something called the energy trilemma. And I'm going to describe that as being, I'm going to simplify it somewhat and say that we have a challenge with reducing CO2 emissions. And this is a challenge that governments around the world have taken up and included in their promises and their policies. Yet nonetheless, CO2 emissions continue to rise. So this is the measured CO2 concentration at the Mount Mauna Loa Observatory in Hawaii. It's up to date till earlier this year, and you can see that it is continuing to rise. So despite all the efforts that have been taking place so far, CO2 concentration in the atmosphere continues to rise. So we've got the challenge of trying to reduce these emissions. The second issue is about providing energy for the world at an affordable rate. And this bottom chart here, the red line shows the oil consumption, the demand for oil that there has been. And just in this past year, we've exceeded 100 million barrels per day oil consumption. And the blue line is showing the price of oil fluctuating, but it remains fairly high. So delivering energy cost effectively is a challenge. And here in the UK, we face particularly high energy bills because there's been a huge move to renewables, such as wind in particular. And so that has a cost. And then the third issue is that trying to deliver energy tied to this, trying to deliver energy at low cost, and in particular, technologies that can help us to meet our energy demand and reduce CO2 emissions are very expensive. So as a subsurface engineer, what can I do about it? And the horizontal axis on these two plots reflect well, I started my career in 1990, so that's the left-hand side. So that's the increase in CO2 emissions over my career. Now, I'm not taking the blame for the increase in CO2 emissions over that period. I don't know how much longer I'm going to be working for. It would be nice if I could get to retirement and at least see that that trend moving over. But who knows? So what can we do? What can I, as a subsurface engineer, do? What can we all do as a community? So the first and obvious thing is that with this increasing oil and gas production, we need to make whatever remaining oil and gas production there will be more efficient and have reduced emissions. This line here is not about to tail over to zero overnight. There's going to be some remaining oil and gas. We don't know how much, but there is definitely going to be. It's still increasing at the moment. We need to make sure that we do whatever we do with remaining oil and gas as with as least impact on the environment as possible. So burying our heads in the sand and saying we don't want to have oil and gas just doesn't work. We'll need to do something about whatever remaining oil and gas there will be. The second thing is that we want to be able to look at using other low carbon energy sources and vectors. The nice thing about oil in particular, but also now with liquid natural gas, is it's very transportable. Electrons are much harder to transport. And so we need to be thinking about other possible energy carriers that there might be there, which would have a lower environmental footprint. And then thirdly, we need to think about what we can do to bring together CO2 storage and hydrocarbon extraction to try and provide more funding for CO2 storage. Because CO2 storage is expensive, then what can we do using oil and gas, income from oil and gas activities to accelerate the amount of CO2 storage that's going on? And it's that I want to concentrate primarily on during this presentation. I will touch on some other topics initially, but I'll move on to looking at the interaction between hydrocarbon recovery and CO2 storage. I'm very privileged to work as part of a large group of people, a large team of people, staff colleagues at Heriot-Watt University, who are all working on aspects of this problem. And this is not an exclusive list, it's just the ones I happen to be working in projects with. We have a fantastic bunch of PhD students that are constantly working through their projects and then renewing as more ones come on. And they are the engine house for a lot of our research. We used to get very frustrated when good PhD students left us. It's good that they're getting jobs in the industry. We've now found a trick, which is to be able to engage with them even after they've left. And we're increasingly finding opportunities to interact with former students in their new work spheres. And so that's a real privilege for us as well. So that's just to give you a little bit of background as to the team. I'm now going to focus on one or two activities that have been carried out by various of these PhD students related to the issue of reducing carbon emissions and focusing mainly on CCS, in fact. So the first one is Patricia here. She was sponsored by Petrobras to come to Heriot-Watt University to do her PhD. She actually goes back to Brazil on Saturday of this week. And she's been working on geochemical interactions that occur during CO2 WAG injection in the pre-salt carbonate reservoirs that they have in Brazil. And to make a comment about those, overall comment about the amount of CO2 that's being stored in those systems in a couple of slides' time. But just to say that we're all well aware that as if you dissolve CO2 in brine, then you acidify the brine, and that increases the amount of interactivity that there might be, especially in carbonate reservoirs. It's not a showstopper by any means, but it does mean that in their production wells, if the water has come into contact with the injected CO2 and it's then come into contact with a rock, which inevitably it does, and it's a carbonate formation, then some of that carbonate rock will be dissolved and will be transported through to the production well and then may precipitate out as a scale in the production well. And so extra attention needs to be paid to managing scale in these wells if these projects are going to be successful. And her work has found out that actually a lot of these mineral reactions are interconnected, they're coupled with each other. So for example, here she's compared a reservoir with a native oil system that's got a relatively low CO2 content with another one that's got a much higher content of 18%. And she's observed in both cases that when injecting alternate slugs of CO2 in water, that calcite, which is the mineral shown in red here, dissolves. Some of these reservoirs also have anhydrite, and that dissolves. And as a consequence of these reactions, dolomite, with the added magnesium present in seawater, dolomite will precipitate. And that happens to a certain extent in the system with 1% CO2 already present in the reservoir. With reservoirs with a higher CO2 content, we get similar looking plots, but actually if you look carefully at the vertical axis, so a negative number means dissolution and a positive number means precipitation of this mineral in this location, actually it's about an order of magnitude bigger change in the case on the right compared to the one on the left. And additionally, as well as the additional calcite dissolution that takes place with the higher CO2 content, now instead of getting anhydrite dissolution, the extra calcium and the sulfate in the seawater is leading to anhydrite precipitation on top of the magnesium, the dolomite precipitation that's taking place. And that will all have an impact on the scaling risk that takes place at the production well. So this is what's happening deep within the reservoir. This has an impact on what happens in the production wells. We also want to learn what we can from looking at conventional oil and gas systems and then taking that forward to new systems such as CO2 EOR ones or other places where we're trying to use other sources of energy. Mojde here is working on a project looking at how certain chemical types, scale inhibitors, can be effective in preventing the types of scale that we're describing in the previous slide. So she's doing a laboratory-based study looking at the efficiency of inhibitors under the types of conditions that might be encountered in these carbonate reservoirs. So this is all related to oil production, but we know that scale happens in other systems as well, and particularly in geothermal wells. And Shabnam is doing experimental work to investigate what we can learn from scale management in oil and gas systems and apply to some of the particularly problematic scale issues, such as the silicate scales that can form in geothermal systems. So that's a matter of taking what we know and advancing it for other systems. Here we've got a couple of PhD students, Ahmad Reza and the recently started Axel on the bottom here, and they're looking at taking techniques that we've developed for modeling geochemical interactions in porous media, such as we might learn from oil and gas systems, and applying them for other processes, in this particular case, hydrogen production or hydrogen generation or hydrogen storage. And adding in to those geochemical reactions, what happens if there are microbiological reactions taking place? And so these become even more complex coupled types of calculations. And the end objective is to try and identify what is the impact of, say, if you're storing hydrogen in a subsurface reservoir, what will be the purity of the recovered hydrogen, taking into account that there may be other processes going on, including biomethanation, as well as mineral dissolution and precipitation reactions. And then moving more specifically into CO2 storage per se, so potentially CO2 storage in aquifers. Tosin here has been working on near well modeling of halite precipitation. So this has been observed already in a couple of CO2 storage projects where dry gas is injected, causes dryout in the near wellbore zone, and loss of productivity has been observed, or damage actually within the wellbore itself has been observed as a consequence of salt precipitation due to the dryout of the brine. And what Tosin has identified in his work is that simply having dry CO2 displace water away from a well doesn't really cause much damage at all. But if there's a zone in the near wellbore area where there's ingress of water, where there's flow of water into that zone, then the salt, the water that's flowing into that dry out zone evaporates, and you get a continuous buildup of salt, and that's where the problems arise. So we might have here's a radial well, here's the well itself, and then we're looking just 4 meters into the formation, and we're tracking in this case the gas saturation. And the red indicates area that's been completely dried out. At the top of this area, because of gravity effects, there's no water, there's no significant salt precipitation. But at the bottom, at the interface between the dry gas plume and the underlying water that's in the reservoir, there's a supply of water due to capillary pressure effects, for example, and due to buoyancy effects, bringing water into this dry out zone on a continuous basis. And that's where we observe precipitation. So this is porosity loss that's taking place at the bottom of this well. And this correlates very well with what's been observed in the field. We're also doing experimental work looking at cores. This is a core that actually, a core flood test, very simple test, which is just taking a core, filling it with brine and pumping dry gas through it. And in fact, very little damage was observed in the core. The change in pressure differential across the core was only marginal. This is work that a colleague Alan Pateta was working on. He took the core out on a Friday, put it on the bench stop, came back on nothing much apparently had happened, came back on the Monday morning, and the core was completely coated in salt. So this is actually very informative. It tells us that water was migrating under imbibition from the center of the core to the edge of the core, which was sitting in the lab. The water that was reaching the edge of the core was evaporating into the lab at one specific location, the outer surface of the core, and leaving behind it this residual salt. And so when the problem of halite precipitation happens in the reservoir, we must have this mechanism of brine being delivered into a zone where drying is taking place, and the imbibition process must provide a flux of water that is slightly less than the evaporative flux. And if that's the case, then the salt buildup will take place. Okay, so let's take a little bit of a step back and think about the oil and gas industry and CO2 injection, and what the relationship is between oil and gas and CO2 storage. So the first thing to say is that we've had over 50 years of CO2 injection into the subsurface formations. This is based on CO2 EUR projects, the majority of which have been onshore in the United States, taking place over these 5 decades. But it tells us that, so some people say, oh, CCS, it's not a proven technology. Pumping megaton scale per annum CO2 into the subsurface is very well known. We've been doing it for most of our lifetimes. It's not in itself. It's not that. I'm going to be careful here. As an academic, you should never say nothing's not that challenging. But it's done fairly routinely. Let me put it like that. And it's definitely, why is it done? It's done because it makes money. It's financially viable when driven by incremental oil recovery. Imperial College London have produced, just over the past few weeks, they've published something called the London Register of Subsurface CO2 Storage. And it's a very useful resource. I encourage you to go and have a look at this website. And on it, they identify all the CO2 storage projects that have taken place since the first project, which was Sleipner in Norway in 1996. And in the intervening period, and the data runs up until last year, and it's constantly being updated, Norway has managed to store 28 megatons of CO2 in aquifers, both in Sleipner and in Snøhvit. And now the Sleipner and Snøhvit are starting to decline. They've now got a new project in the Northern Lights. So it's been sort of the order of a megaton per year, just perhaps a little bit less, proving that that scale of storage in aquifers is viable. And Equinor, who've been doing these projects, it's been cost effective for them to do this. So they've been able to avoid paying taxes on CO2 vented to the atmosphere by injecting it into the subsurface. And the process of injecting it into the subsurface costs them less than the tax that they would be paying if they were venting it. So it makes them money. It makes money sense for them to do it. In a shorter time period, in the Brazilian pre-salt fields that I mentioned earlier, they've actually managed to store 68 megatons of CO2 by the end of 2024. And the target is to reach, I think, about 80 megatons by the end of this year. So they're really ramping up their CO2 injection. Now, this is part of EOR projects, but again, it's driven by the necessity not to vent the CO2. So these fields are some 300 kilometers from the shore, and it would not be viable for them to export the natural gas that is produced along with the CO2 all the way to the shore. So they separate it out, and rather than venting it, they re-inject it into the subsurface. So it's complete storage of the produced CO2 effectively. And to date, some 385 megatons of CO2 have been stored since 1996, of which, and here's an important point, of which 85% has been associated with EOR projects. So we are storing CO2, but in order to do so, we need the income that comes from additional hydrocarbon recovery. And obviously the challenge there is that the incremental barrels of oil that are produced will in themselves result in whatever half a megaton of CO2, half a ton of CO2 emitted per barrel of oil, more or less. So there's a challenge, and perhaps the challenge is to see if we can inject sufficient CO2 that we're effectively producing oil for which the CO2 emissions have been accounted for before the oil is actually consumed. But anyway, the main point is that industrial scale CO2 storage is taking place today. It's often driven by regulation, but it adds economic value to the operators. And so the question for us is, how can we couple oil and gas production to affordably drive down total emissions through coupling them to CCS projects? So I just want to talk a little bit around CO2 storage in hydrocarbon active hydrocarbon basins, and things that we need to think about. And I'm going to talk about some lessons learned, some things perhaps to avoid, and then some synergistic opportunities that might arise. So let me start by describing a project that looked at CO2 storage in the Captain Aquifer. Now, the Captain Aquifer is one of the licensed areas in the UK North Sea that's licensed for CO2 storage, and it's actively being looked at as a potential CO2 storage site. It's not one of the track 1, but it would be one of the track 2 projects if it were to go ahead. And in the Captain formation, so this is a system that's maybe about 150 kilometers from west to east. There's already a fair amount of hydrocarbon activity going on. So there are various fields: the Goldeneye field, the Hannay field, Atlantic Cromarty fields. There's the Captain field, there's the Blake field, and so on in this system. So it's already an active area. So the question is, what are the potential interactions? And looking at modeling CO2 injections into the Goldeneye field, which was a target at one stage, and seeing where the CO2 would migrate to and how much CO2 could you inject before it might start interfering with some of the other hydrocarbon activities in the same system. But actually, more importantly, is the pressure response of the system. And I say more importantly because the pressure response travels much further than the actual molecules of CO2 themselves will travel. And that pressure response could be quite important for other actors in the area, including potentially other CO2 injection sites. So what if we were to take the Goldeneye field here and to use it as a CO2 store, and then at some later date, someone licensed another area of the same system essentially, but at some distance for CO2 storage. Could the fact of CO2 injection in the first site, perhaps without the CO2 actually migrating all the way to the second site, still have an impact on the second site because pressure space, if I can use that term, is taken up by the injection at the first site? So what we've done is we've run some calculations. We've taken a history matched model with the various fields, the Hannay field, the Goldeneye field, production from the Atlantic and Cromarty gas fields, from the Blake oil field. We've taken a line, so imagine this red line here is a piece of string, and so we've taken it through the model system. Now take this the left-hand piece of string in your left hand and the right-hand piece of string in your right hand and pull it tight, and you'll get this line along here. So this is our path along what's called the Captain fairway. And on the y-axis, we're plotting pressure in megapascals. Now, gas production started from the gas and condensate production started from the Goldeneye field in 2002. So let's take the system at hydrostatic equilibrium before the onset of production. Now, because the system is dipping from shallower in the west and deeper in the east, the hydrostatic pressure is increasing. But this is just simply hydrostatic pressure. There's no flow taking place at this point in time. We then have 9 years of production of gas and condensate from the Goldeneye field, and you can see that reduces the pressure at the Goldeneye field by something of the order of 10 megapascals. But it's not just a local pressure loss. Actually, the pressure loss is felt all the way up the fairway. So that's an important point to bear in mind. Pressure, although the gas was actually located close to the in the field, close to the wells, the impact of the pressure changes were felt much further away. So this project was actually looking at the potential for CO2 injection in 2016. So we run the model from 2002 to 2011, looking at production. We then have to shut the system in for 5 years before the prospective CO2 injection in the year 2016, as the calculation was done. Did the system stay completely static? Well, no. Our production had created a disequilibrium in the system, and therefore we have a process called aquifer recharge, with water moving from the neighboring zones back in, filling up the pressure hole, as I refer to it, in the Goldeneye field. And obviously, the longer that we delay the start of CO2 injection, the more that pressure will increase in the target field. Okay, we then assumed that we would start injecting CO2 at the rate of 6 megatons per annum into the 5 wells in the Goldeneye field, so quite a high rate of injection just to test the system. And we found that if we inject it for 5 years at 6 megatons per year, so that's a total of 30 megatons over that 5-year interval, we would fill the system back up in the sense that we would return the GoldenEye field back to its original hydrostatic pressure. So depending on what your constraint is, if you want to limit the pressure increase in the system, you would say that the storage capacity in this field would be 30 megatons. Of course, if you were to inject at a lower rate, if you weren't to inject at 6 megatons per year, but you're only to inject at 1 megaton per year, you could probably inject more because the pressure would dissipate out during the injection period. So there's something to think about in terms of injection rates. We ran the calculation forward just out of interest. Actually, what we're really particularly looking for is at what point will we start to see an impact on the pressure at site B. And so we ran it forward for a further 5 years and then a further 10 years. And we could see the pressure at the GoldenEye field would actually get quite high before we'd actually take site B back up to its original pressure. It had actually seen about a 1 megapascal pressure drop because of the production in GoldenEye. So that 1 megapascal was recovered, but only after about 90 megatons of CO2 was injected. And we'd have to actually inject considerably more CO2 in this calculation, going up to 180 megatons, before we'd start to exceed the initial pressure at site 2 before any injections started at site 2. But you can see that if you were to do this, then we could actually lose some injection capacity at the second site. So although these sites are perhaps some 50 kilometers apart, they clearly could interfere with each other. And so we can normalize that pressure change by subtracting from the initial value. You can see that 10 megapascal pressure decrease during production, perhaps 3 to 4 megapascal pressure loss again or build up during aquifer recharge, and then with the 30 megatons taking the system back up to its original pressure. So what can we say? We can say that natural gas production creates increased storage capacity, so that's good. Injecting into depleted gas fields has its risks. There are challenges with hydrates and phase change taking place in the system, but it does increase the storage volume potential. We also note that the pressure footprint propagates much faster and much further than the CO2 footprint, and that the regulators will need to consider the impact of pressure footprint. So certainly in the North Sea, pressure is not a commodity that the regulator particularly considers. It's first come, first serve. If you've got two adjacent oil fields that share a common aquifer, the regulator will not dictate how much water can be taken out of the aquifer in order to support production from one or either of the fields. This will not be the case with CO2. The regulator, I think, is now very well aware that they will have to take account of, because they will be licensing a certain storage amount, that amount will decrease if the pressure in the system increases because of a neighbor's activities. Okay, the second example I want to use is based on work that's been carried out by actually someone that's on the call, Matteo De Luca, during a short period that he was here at Heriot-Watt University during his PhD. And he took a basin-wide look at, so this is the Silverpit Basin off the coast of the east coast of England, and he looked at the various license areas that are in here, and he said, okay, how much CO2 can we store in the system, and what will be the pressure impact across the entire basin? So the calculation you're about to see is based on an assumption of 14 megatons per annum being injected over a 50-year period into 6 license areas in the North Sea. And he's going to calculate both the CO2 migration and also the pressure propagation. And then run the model for a further 5,000 years. So just to get your eye in, this is the area that we're looking at. Sorry, this is in blue is the area that we're looking at here in the southern North Sea here. And for those of you who are particularly familiar with this, this is license number 1. So the NEP, the Northern Endurance Project, this will probably be the first CO2 injection site in the offshore in the UK. And so he's run the calculation to look at CO2 injection at these various locations, trying to ensure that the CO2 remains within the various license areas that are outlined in white, but also tracking the pressure changes that take place. And you'll notice that with the Northern Endurance project, there's actually an outcrop to seabed quite close by. And so we assume that outcrop is open, and we allow for pressure dissipation out through the outcrop. What would be the implications of that? So he took a cross section going through the Northern Endurance project, going through the outcrop in the southern part of this area. So that's that cross section there. It's almost 80 kilometers in length. And again, he's looked at the pressure change that would take place from the initial state. And he's done the calculation based on 10-year jumps. So we've got increase in pressure in jumps in the solid lines every 10 years over the 50-year period. So obviously the maximum pressure at the end of that period. The pressure doesn't increase at the outcrop, so the assumption is it's a constant pressure boundary condition. Fluid can flow across this into the ocean, maintaining the pressure constant. So seeing a maximum pressure increase of perhaps some 40 to 45 bars taking place round the injection wells in the Endurance project. But then look at how long it takes for the pressure to decrease. So here we've got 10 years in the dotted lines, 20 years, a century, 5 centuries, a millennium later, we're still seeing the effect of the CO2 that was injected over that 50-year period. And it only really takes till 5 millennia later before there's still an effect because of the actual CO2 itself, but the rest of the system is returned to original hydrostatic equilibrium. That's a long time for the whole system to re-equilibrate. And this chart here is showing the amount of water that flowed out through that, would flow out through that subcrop with that total amount of injection, not just in the Northern Endurance project, but across the whole of this basin. Interestingly enough, the maximum amount of water that would flow out would be something like 3,500 cubic meters per day. Well, you get 3,500 cubic meters per day water flow rate from a single well. So it's a fair amount of water, but it's not, by North Sea standards, it's not actually a huge amount of water. Also note that the peak occurred in year 64. That's 14 years after stopping injection. But the flow through that would continue for millennia. And even after 5,000 years, there'd still be a trickle of 40 cubic meters per day of water flowing through that. So we have to bear in mind that these pressure changes may propagate quite quickly, but they become established, but their impact may last for decades, centuries, even millennia. Okay, things to avoid. Let's not say avoid, but let's say things to watch out for and be careful of. So going back to the model of the Captain system, and now saying, okay, we're going to be injecting CO2 into a system which has got some depleted fields. It's got 2 depleted gas fields and an oil field, the Blake field. It's still under water flood, but it's almost come to the end of its natural life. What happens if we inject CO2 into such a system and the CO2 plume migrates into one of these stranded or bypassed hydrocarbon zones? So we ran the calculation assuming no mixing between the CO2 and, let's just say for this, say we've got natural gas, say we've got methane in these 2 accumulations here. So we've got two CO2 injection wells, and we're tracking, what we're actually plotting here is the gas saturation, and we're plotting that gas as it goes into these 2 zones and then is migrating up dip. And our constraint is that the CO2 that we inject does not cross the storage complex boundary, which was arbitrarily picked at this point here, that the CO2 it's injected does not cross this boundary within a 1,000-year period. And so the calculation was run, and it was identified that something of the order of 95, 96 megatons of CO2 could be injected here without breaching that constraint, if we assume no mixing. However, if we assumed mixing, that constraint would be broken within 300 years. So the plume would actually reach this boundary within 300 years as opposed to 1,000 years. So what's going on here? And in fact, if we continue the simulation for the 1,000 years, then that plume will travel much, much further. So what's the issue? So this plot here is showing the density of CO2. And I apologize, we're using pounds per cubic feet here, but it illustrates illustrates the point of what's happening. So we have, in this case, there's no mixing between the CO2 and the methane. And so the plume is a density at this pressure and temperature of this system. It's about 40 pounds per cubic feet. Now, to get your eye in, water has a density of 64 pounds per cubic feet. So you've got a 25 pound per cubic feet density difference between CO2 and water here. In the system where there was methane present and where the CO2 is mixing with the methane, we notice that the density of the plume is much lower. It's somewhere in the 20 to 25 as opposed to 40 to 45 pounds per cubic foot region. So what do we know? Well, we know that CO2 is denser than methane, or methane is less dense than CO2. So the mixture, if a CO2 plume comes into contact with methane, the mixture will be less dense than if it was pure CO2. And that means the buoyancy force will be greater and the CO2 will be driven up dip faster. Something else going on though as well. There's two other things going on, in fact. The second is that the viscosity of methane is lower than the viscosity of CO2. So we're actually increasing the mobility. The mixing of the CO2 with the methane is increasing the mobility, the ease with which the CO2 rich phase, might term the gas phase or the supercritical phase or whatever it is that contains the methane also, the mobility of that is greater. It's going to travel faster. So there's a greater buoyancy force, there's a greater mobility. The final thing to observe here is that the plume here has actually got a very low density. It's only got a density of about 10 to 15 pounds per cubic feet. That's the density of the methane. So I'd say all the CO2 has been stripped out of the plume. And the reason for that is that CO2 is soluble in water, whereas methane is very, very low solubility in water. So as the plume is migrating up dip, CO2 is dissolving in water, but leaving methane in the plume. And so the plume is effectively becoming rarefied. It's becoming purified, a pure methane plume. Interesting question here. What crosses the boundary here, there might not actually be any CO2 in it. It might just be a plume of methane that's been displaced out of the previous trap. Are we in conformance with the regulations that said that in 1,000 years, or our assumption that we should make sure none of the injected CO2 crossed the complex boundary within the 1,000-year period? Interesting question. So this slide just captures those points about the density difference, the viscosity difference, and the fact of CO2 dissolution in the brine, but the methane does not. And so all these factors together mean that the plume travels further, faster, and becomes a pure plume of CO2. And then there are questions about how do you model the viscous fingering that will take place as this plume is changing its properties through the system. That's an area of active investigation. Okay, let me finish off the presentation by talking about some synergistic opportunities that may arise. So here's a model of a system in the North Sea. It's a fairly large oil field, and we looked at replacing water injection as the main recovery process with CO2 injection. And the black line here is showing the projected oil recovery that would take place. So this calculation was done 15 years into the life of the field, while it still had another 25 years to go. And the projected recovery factor was actually quite good. It's 55%. Replacing at least not all, but some of the water injection with CO2 injection would allow a somewhat like 5% increase in the oil recovery in a shorter period, actually in 5 years less than the full water flood. And in that process, we looked at various options of putting injection wells further down dip and having all the injection wells converted to CO2 injection wells, and having a mixture and so on. And this one here, where with some water injection, proved to be the best. With that one, you're still getting, so it's the blue line here for net CO2 stored, 53 megatons of storage. So 5% increase in oil recovery and 53 megatons of CO2 storage. So you can see the thinking here. There's a potential, in fact, the problem here is actually insufficient supply of CO2. I'm fairly sure the operator would have looked at this quite seriously if they'd been confident that there would have been enough CO2 delivered to them to carry out the project. So I'm going to finish off just with three snapshots of three projects that our PhD students are currently looking at. This is Ahmed, and he's working in Saudi Arabia, and he's looking at the potential for using CO2 to recover oil from naturally occurring residual oil zones. So residual oil zones are zones where there's been a natural water flooding process, maybe due to tilting or some other natural process, and there can be very large volumes of oil. It's residual, so it's immobile, but it can be displaced by CO2. The challenge with that is the first thing you produce in these systems is not oil, but water, because it's water, it's a mobile phase. But the opportunity is that you could end up using a lot of CO2 to recover the oil. And so the barrels of oil produced per ton of CO2 injected ratio might be quite low, but that's a positive thing for us, could be a positive thing. If the oil recovery is financially justified, then storing a large volume of CO2 would be a positive thing to do. The second one is a student from South Africa who's over here in Edinburgh, and she's working on looking at different systems and comparing CO2 storage in an aquifer versus taking that same geological structure and having it as a depleted gas field, and also having that same structure and having it as a depleted oil field. And for example, can you take advantage of the greater compressibility of the oil compared to water? Will that mean a greater storage capacity if the system has got residual or bypassed oil in it, say? And also taking advantage of the fact that CO2 solubility in oil is much higher than CO2 solubility in water. And there are a few systems in South Africa that are amenable to comparison of this nature. And then the final project is an interesting one, looking at, from Farah here from Kuwait, looking at the potential of temporary storage of CO2. Well, why would you want to do temporary storage of CO2? The answer is that they have a potential CO2 EOR project that may come on stream in 10 years' time. And currently, they have a power generating plant that's generating about 2 megatons per annum of CO2, which has just been vented into the atmosphere. What if that CO2 were to be captured now, stored temporarily in an aquifer, and then back produced to support the EOR project when it comes on stream? So that would be 10 years of avoided CO2 emissions into the atmosphere, paid for out of the prospect of incremental oil recovery. And then once the CO2 EOR project is finished, you've now got two geological structures, the oil field and the temporary aquifer storage system, which both have got infrastructure that allows CO2 to be injected into them. So they could both be converted into CO2 stores. So this is an interesting project just started in the past year. Okay, I want to finish off by saying that we need to work on improving conventional oil recovery processes, improving the efficiency, reducing the carbon footprint associated with these, because they will be continuing, and they will be continuing for years and decades to come. It's not going to suddenly stop. We need to apply what we can learn from oil and gas recovery processes to other fields associated with the subsurface and energy. And we need to think particularly carefully about how can we ramp up CO2 storage by, I'm going to use the term here, piggybacking it off oil and gas recovery. So how can we use oil and gas recovery to finance more CO2 storage? I'm particularly looking for synergies. And one of the important factors with CO2 storage is that pressure is a commodity, but we tend to build up the pressure too much. Actually, in hydrocarbon recovery, pressure is also commodity, but we're trying to draw down pressure. Can we use the two of them together? Can we use hydrocarbon extraction to increase CO2 storage capacity by pressure management? And can we use CO2 injection to maximize hydrocarbon recovery, again by pressure management, somewhat replacing water flooding? And then can we think about phasing CO2 and hydrocarbon recovery to try and maximize the storage potential? So with that, I want to thank the funders of the research and of the PhD students that we've been working with at Heriot University, and thank you for your attention. And be very happy to take any questions if there are any.
Thank you very much, Professor Mackay. It was very interesting, more than interesting for myself. And I hope that everybody has enjoyed that as much as I did. So we would have some time for questions. I think we do have some question already in the box.
Okay, so I'll take them from the top, will I? Chris Jackson, in the GoldenEye case, might you possibly reach lithostatic pressure and thus induce leakage if you kept? Yes, absolutely. Yes. So it was a bit of an experiment that we can perform with a simulator to keep on injecting beyond the original pressure. I'd imagine in systems that have been depressurized due to gas production, the target would be to return them perhaps back to their original or close to their original pore pressure and not exceed that. So yeah, the experiment was carried out just to see how far away the pressure plume, sorry, the pressure response might be felt. But in practical terms, I don't think you'd ever be looking at storing 360 megatons, 180 megatons of CO2 in the GoldenEye field. Could anything be done to the CO2 pre-injection to try and mitigate the potentially negative impacts of CO2 methane mixing and thus the rate of CO2 plume migration? So that's a good question. I suppose one thing to think about would be just having your injection wells in a different location to avoid the mixture. Actually, the presence of the gases, of the natural gas in the depleted field is beneficial in that it's much more compressible than water. So the problem just arises when you get the actual mixing of the different fluids. I don't know if you're thinking about something else like trying to viscosify the CO2 to reduce its mobility. Perhaps there are other things that can be considered.
Yeah, it was to do with how you could dose it somehow, really, ahead of time. But it's just a thought.
Yeah, I think well, precisely. I think we need to be a little bit more imaginative about CO2 injection and the things that we can do to maximize storage capacity and security. And there may be things, I'd say, even just understanding the impact of impurities. So relatively small amounts of impurities, as will inevitably occur, can change the phase behavior of a CO2-rich stream, particularly when you're close to the critical point. And so even just perhaps even just managing what might be other impurities that you might spend a lot of effort removing, they might actually also have some benefit. Alexander, thank you for your comment. I think it is important that certainly true of a lot of academics, we've kind of concentrated on looking at single systems, pure CO2 injection at a constant rate. We need to be thinking about, okay, the CO2 injection is actually taking place sometimes in a busy environment. It can be a busy surface environment with wind farms and so on, making it difficult to monitor. It can be a busy subsurface environment with other activities ongoing or having taken place in the past. And we can't look at CCS in isolation. However, that does also, as well as bringing risks, it also brings opportunities to us. And I think it's important that we consider this. It's also important that we consider, as I was mentioning, the impact of impurities, the fact that the impurities, so if you have a cluster system, for example, and you've got various industries supplying into a hub, that the composition of the injected CO2 and indeed the rate at which the CO2 becomes available may vary over time. And so we need to take account of these factors as well. What happens if you're heavily reliant on power generation system, and it suddenly shuts in for whatever reason, and you have to stop injection. Or what happens if you're also injecting CO2 from a cement plant, but the balance of impurities changes very suddenly when you stop the power supply source, and then all you're injecting is the CO2 from the cement plant, etc. And we also need to think about ship delivery of CO2. So what happens if should we be injecting the CO2 as fast as possible from the ship, and then so it can get away and collect some more CO2? Should we have temporary storage at the wellhead, and then gradually displace the CO2, offload the ship into the temporary storage, and then more gradually displace the CO2 into the subsurface system, which is effectively what's happening in the Northern Light projects, albeit there's some distance between the temporary storage and the final subsurface system. Tofik, analyzed geomechanical effects since depletion. Well, have you? It's a question. Have you analyzed geomechanical effects since depletion can cause changes in effective stress? Absolutely. So oftentimes when we look at water flooding of oil reservoirs, we're not really changing the overall, locally we're changing the pressure, but we're not changing the overall pressure of the system. And we tend to assume that we can get away with ignoring geomechanical effects. Perhaps in the near injection well, if there's cooling and so on going on, that has to be taken into account. Also, we often ignore geochemical effects in water flooding in reservoirs. I think with CO2 storage, geomechanical and geochemical issues don't necessarily need to be a showstopper, but they need to be addressed. And the regulator will require to see that they have been addressed in any license applications or applications to inject. There are interesting questions about the impact, for example, of thermal effects. If you're injecting colder CO2 into a formation, what's the risk of that thermal front reaching faults and contributing, along with the pressure increase, to fault reactivation? So that could be a significant risk. So there are lots of things that need to be thought about in more detail associated with CO2 storage that perhaps we get away with a lot of time in hydrocarbon recovery systems with not thinking so carefully about.
Okay, I
Nestor.
think we have time with the last question.
Please allow me to answer Nestor. Nestor's a former student
Okay.
of ours, so it's nice to hear from you, Nestor. So the question about scale in pre-salt carbonate reservoirs, is it present mainly in the reservoir, or will it occur inside the reservoir? Well, so that's a really interesting question. The evidence so far there's been a lot of CO2 injection, as we say, almost 80 megatons of CO2 injected into these subsurface systems, mainly in association with water injections, so as part of CO2 WAG processes. There's very little evidence of damage to injection wells. So that suggests that there will be geochemical reactions that are taking place in the rock, but the mass of rock is so great, and the pore volume is so great, that actually these changes are marginal deep within the reservoir. The big risk comes when you have brine that is saturated with carbonate minerals reaching the production well, and then you're in a zone with a relatively small volume, the tubing volume, and big changes in pressure, temperature to some extent, but big changes in pressure within the tubing volume cause a big change in the equilibrium and the precipitation of a large amount of these carbonate minerals in a relatively small volume over what can potentially be a fairly short period of time. And so they have seen significant problems in production wells. Thank you for the question. I apologize for going over time, and that's perhaps limited the question.
Thank you very much. Thank you very much for this fantastic presentation, and also thank you for accepting our invitation. And thanks to all the participants for joining us, and I hope that you all enjoyed.
Thank you.
Yes.
Goodbye.
Yeah, I want to say something before we finish. So thank you all for joining us today, and a special thanks for Professor Eric Mackay for sharing these valuable insights, as well to the EAGE Technical Community and CCS for making this session possible. We hope you all found the webinar informative and engaging. And if you would like to stay tuned for future activities or become part of our CCS community, please scan the QR code on the screen and request to join our LinkedIn group. Okay, so thank you once again, and we look forward to seeing you at our next event.